Hello everybody, myself Jyoti, and last time we discussed about the crystal defects. I gave you just general introduction about the crystal defects. So there are three types of crystal defects like point defects, linear defects, and planar defects. So today we are going to focus mainly on point defects only. So point defects may you have again different types. So one of the type of point defect is vacancies. So first we will focus on vacancies. Now when we talk about a perfect crystal with the perfect crystal is a crystal with a regular arrangement of atoms, but it cannot exist. There are always defects, and the most common defects that we know are point defects. Now, this is especially true at high temperatures because at high temperatures, atoms will start vibrating about their mean position more frequently because we know that this atomic vibrations, they are temperature dependent. Temperature increase kar diya, so these atoms will start vibrating violently and they randomly change their position, leaving behind empty lattice site. When these atoms they start vibrating with very high energy, then they empty that, they move to some other position, and there is a vacancy, there is an empty space which is created in the lattice site, and that empty space it is called as vacancy. In most cases diffusion can only occur because of vacancies. So here you see in this diagram, एक minute, if you see in this diagram, then here in the middle you can see there is a vacancy. Okay, now, how many vacancies are there? The higher is the temperature, more often atoms are jumping from one equilibrium position to another, and larger number of vacancies can be found in a crystal. Actually, the number of vacancies increases exponentially with absolute temperature. Remember this, and can be estimated using the Boltzmann distribution. Boltzmann's distribution is Nv equals to Ns exponential minus Ev upon kBt, where Ns is the number of regular lattice site. कितना lattice sites है? That is Ns. Kb is the Boltzmann constant, and Ev is the energy needed to form a vacant lattice site in a perfect crystal. If an atom has to form a vacant lattice site, it has to jump from that position to some other position. वो jump करने के लिए भी atom के पास कुछ energy होना चाहिए. That energy is Ev. Now using this simple equation we can estimate that at room temperature, suppose copper है, if we take the example of copper, at room temperature copper में there is one vacancy per 10 raised to 15 lattice atoms. Imagine now if we increase the temperature of copper, कितना increase करना है? Just below the melting point of the copper, then you can see that there is one vacancy for every 10,000 atoms. So you can see how is the effect of temperature on the vacancy. So there are the lower end estimations. A large number of additional vacancies can be introduced in a growth process. Like when we are talking about creation of vacancy, we are focusing on only one factor, that is temperature. Temperature increase हो रहा है तो vacancies create हो रही है, but it is not the temperature only which can create vacancy. Vacancies can be created because of many reasons. So the other reasons are vacancies can also be introduced in a growth process. जैसे कि growth process में we have plastic deformation या quenching from high temperature to ambient temperature. ये सब process के वक्त भी vacancy create होता है, but mainly we are focusing on temperature dependent vacancies which are created. Now, how often do vacancies jump? In order for atom to jump into a vacancy site, suppose vacancy create हो गई, and if another atom has to jump to that vacancy site, then it needs to possess energy, and that energy it is called as activation energy for vacancy motion. Now see this diagram, there is atom this side and there is vacancy this side. So if this atom has to jump to this side, then it has to possess the energy Em. Look at the graph, Em. So that is called as activation energy. Now the average thermal energy of an atom is usually much smaller than the activation energy Em, and a large fluctuation in energy is needed for a jump. The probability of such fluctuation or frequency of jumps, how many atoms are able to jump to that vacancy site, that is given by Rj, and it depends exponentially on temperature, and it can be described by an equation, and that equation it is called as Arrhenius equation. So Arrhenius equation, it is Rj equals to R0 exponential minus Em upon kBt. Em it is activation energy, Kb is Boltzmann constant, T is temperature, Rj is frequency of jumps, how many atoms are able to jump to the vacancy site, and R0 is a constant. So let us talk more about point defects. So point defects basically they are of four types. One is vacancy, second is interstitial, third one is Frankel defect, fourth one is Schottky defect. तो इसमें से interstitial भी जो है उसके फिर से थ्री टाइप्स है, self interstitial, interstitial impurity, substitutional impurity. Okay. Now, what are interstitials? Interstitials are basically atoms that are squeezed in between regular lattice sites. Interstitials क्या है? Suppose there is a regular arrangement of atoms in a solid. In between कोई atom घुस गया. That is called as interstitial. Now, self-interstitial क्या है? If the interstitial atom is of the same species as the lattice atom. Suppose मैंने Zn का crystal लिया, zinc का crystal. सारे zinc के atoms है और one atom of zinc, second atom of zinc, third atom of zinc, ऐसे there is a regular arrangement of zinc atoms in a zinc crystal. In between, suppose और एक zinc atom additionally, if it is placed between 1 and 2, first and second zinc atom extra, so that is called as self-interstitial. So it is not some other atom has come, it is the atom of the same species of the lattice atoms. It is called as self-interstitial. So creation of a self-interstitial causes a substantial distortions in the surrounding lattice and cost more energy as compared to the energy for creation of a vacancy. So vacancies are more common as compared to self-interstitial because self-interstitial के लिए और भी ज़्यादा एनर्जी लगता है. And under equilibrium conditions, self-interstitials are present in lower concentration than vacancies. Now, what is interstitial impurity? Suppose दो atoms के बीच में, if there is a crystal and if suppose there is an additional atom, interstitial यानी एक extra atom आ गया. अब वो एक extra atom suppose उसी atom उसी क्रिस्टल के एटम का है, देन इट इज सेल्फ इंटरस्टिशियल. बिकॉज सपोज Zn का क्रिस्टल है, उसमें कॉपर का एक एक्स्ट्रा एटम आ गया, देन इन दैट केस इट इज कॉल्ड एज इंटरस्टिशियल इम्प्योरिटी. फॉरेन यूजुअली स्मॉलर एटम्स लाइक कार्बन, नाइट्रोजन, हाइड्रोजन, ऑक्सीजन, ऐसा कुछ बीच में आ गया तो देन दिस काइंड ऑफ इम्प्योरिटी इफ इट इज देयर, इट इज कॉल्ड एज इंटरस्टिशियल इम्प्योरिटी. दे इंट्रोड्यूस लेस डिस्टोर्शन टू द लैटिस एंड are more common in real materials and more mobile. So as compared to self-interstitial, interstitial impurity is more common. Now next is what is substitutional impurity. अभी क्या हो रहा था, there is a periodic arrangement of atoms और in between atoms आ रहे थे, मे बी वो सेम ही एलिमेंट का क्रिस्टल का एटम या फिर कोई फॉरेन एटम. अभी क्या हो रहा है, देर इज सपोज देर इज अ पीरियोडिक अरेंजमेंट ऑफ एटम्स और उसमें से किसी लैटिस साइड पे वो एटम नहीं है बट कोई फॉरेन एटम रह रहा है, इन बिटवीन नहीं आ रहा है, वो उस लैटिस साइट पे आ रहा है. सो इफ द फॉरेन एटम रिप्लेसेस और सब्सटीट्यूट्स फॉर अ मैट्रिक्स एटम, जो रेगुलर अरेंजमेंट ऑफ एटम है उस एटम की पोजीशन पे सपोज फॉरेन एटम आता है कोई, देन इट इज कॉल्ड एज सब्सटीट्यूशनल इम्प्योरिटी. ओके, सो लुक एट दिस फिगर केयरफुली एंड देन यू विल अंडरस्टैंड. सो फर्स्ट नंबर 1 लिखा है, if you can check, see this number 1, यहाँ पे there is look at the number 1, there is no atom in between, so that is vacancy. Look at number 2, there is atom but same atom ही है, जो periodic arrangement of atom है वही atom वहाँ पे extra आ गया है, so that is self interstitial. Look at number 3, number 3 पे कोई दूसरा atom आया है, it is not a green atom, some blue atom, smaller one, it has come to that place, that is called as interstitial impurity. And 4th and 5th if you check, so वहाँ पे वही एटम होना चाहिए था, बस वो एटम की जगह पे फॉरेन एटम आया है, then that is called as substitutional impurity. Okay, so this is all about the point effect. Thank you so much, and in next class we will study about the planar defects. Thank you.